In section 2 of chapter 6, we're going to be further dissecting rational equations. We're going to be taking a different approach. Thus far, we've found the non-removable and the removable discontinuities, aka the vertical asymptotes and the point discontinuities. Those were key characteristics about the graphs of rationals. We're still not there yet to graph them completely, but I want to point out another feature you may or may not have noticed. Now, I'm not requiring that you write these down. I'm mainly focusing on you recognizing from the graphs a key characteristic, and then I'm going to show you algebraically how to find it. So for problem number 1, I have the equation in case you want to type it in Desmos and fact check me. But you should note at this point, since we are dividing by x minus 2, and it would not eliminate with anything on top, at x equals positive 2, we would be dividing by 0, which is why at 2, there is a vertical asymptote. That is to say, that asymptote is a location that the graph is going to get closer and closer to, but technically never intersect with. If you look at the graph, you might also notice there's a horizontal asymptote. That's what we're going to be focusing on today. There's a horizontal asymptote for this one at y equals 0. It gets closer and closer to the x-axis, but it technically will never ever touch it. Now, horizontal asymptotes are not strictly stuck on the y-axis. They can move up and down depending upon different factors. For example, problem number 2, g of x. I have 2x squared plus 2x, all divided by x squared plus 3x. If you were to graph that, there would be a point discontinuity at x equals 0, because they both have a GCF of x, so they would eliminate. It would be removable, making a point discontinuity. However, the discontinuity of x equaling negative 3 still is going to be a non-removable, meaning there's a vertical asymptote there. But there's also a horizontal asymptote at y is equal to 2. These are key features that all technology, at least at this point, does not know how to show you. If you use Desmos, a graphing calculator, even the fancy TI-89s, they do not show you where asymptotes are. You have to be able to recognize when they're going to show up and where they're going to be. This is a gap that thus far technology hasn't bridged yet. So how do we find horizontal asymptotes? There are 3 categories for rational functions. Category number 1, if the degree of the top is greater than the degree of the bottom, then there will be no horizontal asymptote. So what do I mean by that? I'm going to do a little example. I'm going to write an equation. A rational function, by definition, is just a polynomial function divided by a polynomial function. What we're going to analyze is the degree of each of those polynomials. So the numerator could be something like x to the third power minus 3x squared plus 2x. When analyzing that polynomial, we don't care about the negative 3x squared, the positive 2x. Heck, even if I put a plus 211. We don't care about any of those terms. All we care about is the first term, and in particular, we care about the power of the variable. This is an x to the third power, so the polynomial on top is a cubic. It's a third degree polynomial. Now, something on the bottom could be something like x minus 1. Notice the degree of the denominator. This is a first degree. This is a third degree. The degree of the top is bigger than the degree of the bottom. Because of that, if you were to graph this example I have written right here, there wouldn't be a horizontal asymptote. Number 2. If the degree of the top is less than the degree of the bottom, then there will be a horizontal asymptote at y is equal to 0. This is the x-axis one that I showed you on the previous slide. So as an example, I can write any rational function I want. I just need to make sure that the degree of the top is smaller than the degree of the bottom. So I can make the top, just keep it simple, 5x plus 1, divided by, I need the bottom to be any power higher. So it could be a second power, third power, fourth power, 513th power. Doesn't matter as long as it's bigger. So x to the third power minus 4x plus 7. Doesn't even have to be factorable. Doesn't have to be a nice equation. You could use decimals. You could use anything you want, as long as it's a real number. But the important aspect is the degree of the denominator, it's a third degree polynomial, is bigger than the degree of the numerator. If that occurs, horizontal asymptote is at y equals 0. The third and final category. If the degree of the top is equal to the degree of the bottom. Then there will be a horizontal asymptote at y is equal to a over b. So as an example, if I have something like 6x squared minus 7x plus 11, all divided by 2x squared plus 8x minus 5. My a value is the number in front in the numerator. So this right there, that's 6, that's our a value. The b value is the leading coefficient in the denominator. So that 2, that's my b value. Therefore, for my example, it'll have a horizontal asymptote at y is equal to 6 over 2. But 6 over 2 is reducible. 6 divided by 2 is 3. So if I was to graph that example I had written, it would have a horizontal asymptote at y equals 3. You'd go up 3, draw a horizontal dashed line, and you'd call it Dunsies. Here's what I'm going to ask you to do in this lesson. I am going to give you rational equations. I'm not going to ask you to graph them yet. I'm just going to ask you to find some of their key characteristics. 2 of them you've already done before. I still want you to find the removable and non-removable discontinuities because it's important to practice that. But additionally, I want you to tell me if there's a horizontal asymptote, and if there is one, I want you to tell me where it exists. Now, the nice thing about horizontal asymptotes, as I just showed you, is a lot of the time, you can just look at the problem and tell me the answer. Like problem number 1, I have a cubic on top, and I have a square on the bottom, so the top power is bigger than the bottom. So I automatically know there's no horizontal asymptote. But again, because I'm mean, I want you to also tell me the discontinuities. So what I could do is factor that into x cubed over x times x minus 3. I would recognize that the x would eliminate with the third power, leaving me with the second power on top. Therefore, the discontinuities, which would be 0 and 3, break into 2 categories, removable and non-removable. The x got removed from the denominator completely, therefore the discontinuity that came from it is going to be a removable discontinuity. And then the discontinuity that came from the part of the denominator that did not get removed, it is a non-removable. It would be a vertical asymptote. Problem number 2, same thing. I have a second degree on top, second degree on bottom. Top and bottom are the same, so that is the third rule. That means that the horizontal asymptote is at y is equal to 4 over 2. 4 divided by 2 is 2. So there is my horizontal asymptote because the degree of the numerator and denominator are equal. In order to find the discontinuities, I need to factor this. So g of x would equal 2x plus 3 times 2x minus 3 all over denominator. You can factor an x out and get 2x minus 3. Then I noticed that the 2x minus 3 and the 2x minus 3 on top and bottom would eliminate. Therefore, my removable discontinuities are when this would be equal to 0. You can set it equal to 0 and solve it algebraically, 2x minus 3 equals 0, or recognize that it's just x cannot equal positive 3 over 2. And then this discontinuity of 0 did not get removed, so for my non-removables, x cannot be equal to 0. And these are the 3 parts for my question number 2. The horizontal asymptote, the removable discontinuities, and the non-removable discontinuities. Lastly, problem number 3. The degree of the top is a first degree. It's a linear function. The degree of the denominator is a quadratic second degree. The bottom is bigger than the top. Therefore, there will be a horizontal asymptote at y is equal to 0. That is the x-axis. In order for me to find the discontinuities, I got to take the function h, and I've got to have to factor it. I could take a 2 out of that. That'd be 2 times x squared plus 12x plus 35. And then that factors again. Into x plus 7 times x plus 5. The x plus 7 on top and bottom would eliminate. Therefore, the removable discontinuity comes from the x plus 7, meaning x cannot equal negative 7 is removable. And then the non-removable is the discontinuity that remains. That's just the x plus 5, which produces a discontinuity at negative 5. And those are my discontinuities. My vertical asymptote, my point discontinuity, and then the horizontal asymptote.